Applications of Differential Calculus, page 10. Number 19. We have this piece of paper cut out in a circle, actually part of a circle, and we're going to fold it into a cone. First of all, it says, show using the sector that arc AC equals theta pi divided by 18. So remember that the formula for arc length is arc length is equal to r theta, where theta is in radians. Now this theta happens to be in degrees, so we need to convert it a little bit. So theta in degrees, we would say theta, and we would divide by 360 degrees, and then we would multiply by 2 pi, and that would convert it to radians. So let's do that. And in this case, the r is this 10 here. So actually we're going to have theta times 10 pi over 360. Actually, it's 20 pi because there's a 2 there. So it'll be theta pi divided by 18. And that's the expression they have here. Okay. So that was part A. Let me rewrite that. It's kind of messy. B. Explain why r equals theta divided by 36. And the r they're talking about now is this r here, the radius of the base of the cone. The r that we put here, and let me write that differently. I'll write capital R or something, is actually this length there, 10. This is smaller than 10, obviously. So we can actually set that equal to this, because when you fold this cone, you can see that this blue line here is actually this blue line here. So we could say that either the blue line is part of the big circle, or it's the full small circle. So we could say it's 2 pi small r, which is this length right there. And then we could say, okay, let's solve for r, and we'll have 2 pi r equals theta pi divided by 18. So r is equal to, we could cancel the pi's, and then we'll have theta divided by 36. Okay. Oh, and there we go. C. Show that h equals that expression there. Okay. Let's take a cross section of the cone. The cone's going to look like this, right? And if we draw the vertical line down the middle, that would be the length, or the height h. And then half of this base is going to be r. And then we know that the hypotenuse is 10, right? Okay. So they want us to find a expression for h. So h can be related to r by Pythagorean's theorem. And then if we want to find h itself, we could say h is equal to 100 minus r squared, square root. And then we can substitute in that expression for r. So now we're going to have square root of 100 minus theta squared divided by 36 squared. Okay, and that's the expression, right? Now, D. Find the cone's capacity V in terms of theta only. First, what we can do is we can write the volume for the cone, which is 1/2 pi r squared h. Oh, I'm sorry, 1/3 pi r squared h. So let's fill in what we know. R we know is theta over 36 squared. And h we know is this expression here, 100 minus theta squared divided by 36 squared. Okay, so that was D. And then it says, use technology to sketch the graph of V of theta. Let's see. So we can type all this expression in there. 1/3 times pi times theta squared, and theta we could say is x squared, times the square root of 100 minus theta squared divided by 36, 100 minus theta squared divided by 36 squared. Okay. And then all that is divided by 36, right? 36 squared, actually. Okay. Then it says to graph that. Let's do a zoom fit. And then it says to find theta when the velocity of theta is a maximum. Okay. Alright, and we only want to graph this from like 0 to 360. Doesn't really make much sense to do larger than that. Okay, and then we're gonna zoom fit again. Oh, there we go. Ah, interesting. Okay, so there it is. There's the point. So let's find that point. We use second calc maximum. There's our left bound. There's our right bound. And obviously you could do this using derivatives. But look at that. You're going to have to use a product rule for this u, and then for this v, it's going to be awful derivative. So the maximum that came up on the screen was r equals 293.9, and the volume is equal to 403. So that's it. Now let's go to the next problem. Hugh can row a boat across a circular lake of radius 2 kilometers at 3 kilometers per hour. He can walk around the edge of the lake at 5 kilometers an hour. What is the longest possible time Hugh could take to get from P to R by rowing from P to Q and then walking from Q to R? So we colored the water path blue and we colored the ground path brown. And then let's call them W and G. And basically what we want to know is like the time it takes to go by water and the time it takes to go by ground, and try to maximize that time. Let's first figure out the distance of W and G. Let's see. Let's redraw our distances here. So like in one case we have a triangle problem, in the other case we have like an arc problem. Okay, the arc problem, let's remember that the angle theta here is going to be half the angle of this angle which starts at the center of the circle. So theta is equal to 1/2 phi. Okay, we know that from 9th grade geometry. And then here we can make two small right triangles from this triangle, and we have theta here, and this is also theta because it's symmetrical. And the whole thing is W, and each side is 2 here. Okay, so can we figure out an expression for W in terms of theta and 2? Well, at least half of W would be easy, right? Because we could just do like a cosine of theta is equal to half of W, which is this blue part here, divided by the hypotenuse 2. So cosine of theta is equal to W divided by 4. So W is equal to 4 times cosine of theta. Okay, and let's see. So that is the distance for W. And if we wanted to figure out the time W, then we could simply take the distance. Let's see. Remember that velocity equals distance times time. So time is equal to distance divided by velocity. So the distance is W and the velocity is 3 kilometers an hour, right? So it's equal to 4/3 cosine of theta is our time for W. Now let's figure out the distance G. We know that using phi, we can figure out the arc length G because this radius is 2. So we know that r theta equals G, or G equals r theta, and we know that r is 2, so it's 2 times theta, theta being in, phi, I'm sorry, being in radians, okay? So G equals 2 phi. And we know that theta equals a half of phi. So basically, phi is equal to 2 theta. And so we can plug that in, and now we have, and I didn't mean to mislead you here. I put theta here, but this theta here is from the formula r theta. So that's confusing. Sorry about that. And so this, G equals 2 phi, time, we can substitute 2 theta in for phi, so that would be 4 theta. So G is equal to 4 theta. And then we could find the time that it takes to walk G by taking G and divide by the velocity of walking on G, which is going to be 5. So now we have and we have an expression for G in terms of theta, which is 4 theta. Okay. So now we can say, okay, the time, we know the time, it's going to be 4/3 cosine theta plus 4/5 theta. And then you're going to say, but that's not a time. It's still got theta in it. But theta is not defined, so you can't give an exact number. You can only give a number in terms of theta. That's the best you can do. Now that we have the total time it takes to walk the blue route and then the brown route, they want to maximize that time. So now what we could do is we could take the derivative of this and set it equal to 0 to find the stationary points. So that would be so dt, derivative of the time, in terms of theta, is going to be 4/3 negative sine of theta plus 4/5. Okay. And then we're going to set that equal to 0. So 4/3 negative sine theta plus 4/5 is equal to 0. And then we'll put 1 on each side, so we'll have 4/3 sine theta is equal to 4/5. And then we could cancel out the 4's, and then we could have sine theta is equal to 3/5. And then the theta is going to be the inverse sine of 3/5. And we can do that on our calculator. Inverse sine 3 divided by 5 0.644. Okay. So it's 0.644 radians. And let me make sure that I'm in radians mode. I was assuming that I was. Yes, I am. Okay. So the theta that would maximize the time of walking that would be 0.644. Then they want to know the time itself. So now we need to substitute in the 0.644. So we're going to have t equals 4/3 cosine of 0.644 plus 4/5 times 0.644. And that'll give us... So I typed all that in the calculator just here. See? And then I'm going to hit enter. And it gives me 1.58 hours, right? Because all the time here is in hours. I forgot to do one more thing, which is to confirm that this is actually a maximum and not a minimum. And the easiest way to do that is to take the derivative dt d theta, which is equal to negative 4/3 sine theta plus 4/5, and to make a sign diagram for it. So we know that the stationary point is 0.644. So just plug in like a number that's above that and below that and see if 0.644 is indeed the local maximum or not. So let's put in a number like 0.3, which is lower, and then we'll do sine 0.3, and that gives us 0.295, blah, blah, blah. And then we multiply that times negative 4/3, negative 4/3, and then we add 4/5, which is 0.8. So that gives us a positive number. So it's positive here. And then we try a number that's above 0.644, like maybe 1. And then, so we'll do negative 4/3 times sine of 1, and we'll add 0.8. And we'll get a negative number, negative 0.322. So it's negative. So you can see from the sign diagram that we're going to go up, and then it's going to be flat here, and then it's going to be down. So that is a maximum, right? And that's what they wanted, a maximum.